All right, welcome to day 2 of polar calculus. Today we are going to learn how to convert between polar and rectangular coordinates, and we're going to do this with both points and equations. So let's get to it. As a warm-up here for example 7, I've got a couple polar curves sketched as well as some equations, and the task at hand is to match the equation to the curve. And I'm going to leave this as an exercise to the viewer. I will give you which ones match, but I do want you to spend some time and figure out why they match. So if you want to pause and try to do it without me giving you the answers, go ahead and do so now. Okay, here's the matches that I came up with, and I'm going to leave it to you to generate some reasons why. We'll discuss it in class when we meet next. Things you might want to look at is how many polar zeros exist in the equation, i.e. how often is the radius equal to 0. You might want to look at how fast is the radius growing, if it's growing or if it's growing and shrinking, oscillating between the two. And let's see. I'll leave those hints there for you. So go ahead and tackle this. Let's move on to example 8. Okay, we are going to learn how to convert between polar and rectangular coordinates. And from trigonometry and the unit circle, we might already know this, that the x-coordinate is equal to cosine theta, or more generally equal to the radius times cosine theta. With our unit circle, we were assuming the radius to be 1, so very often we just wrote x equals cosine theta and y equals sine theta. From that, we can extract other useful equations, like x divided by radius is equal to cosine theta. And we can also extract y divided by radius is equal to sine theta. And those equations will get used fairly regularly in converting. And when we want to take a rectangular equation and convert it to polar coordinates, what we can do is we can say the radius is equal to the square root of x squared plus y squared. And that's derived from our, or can be derived from our equation of a circle, x squared plus y squared equals radius squared. So solve for r. We can also use the unit circle to figure out what tangent of theta is, and so that's going to be y over x. So, or we could say theta is the inverse tangent of y over x. So let's go ahead and do this with example 8a. We have a polar coordinate. This is polar, and we want to go to rectangular. So the way we do that is we state that x is equal to r cosine theta, or I'm going to zoom in here so we can see this better, or x is equal to, in this case, 2 cosine of 5 pi over 6. And evaluating cosine of 5 pi over 6, we can use the hand trick on get equal to 2 times negative root 3 over 2. The 2's cancel, and our x-coordinate is negative root 3. Now we go to our y-coordinate. We know that y is r sine theta. Y and sine travel together. And so we can say y is equal to 2 times sine of 5 pi over 6. And our unit circle tells us sine of 5 pi over 6 is equal to 1/2. So 2 times 1/2 is 1. So there we go. There's our rectangular coordinate that is equivalent to that. Okay. Graphically, you could think of the polar coordinate. We go to the angle of 5 pi 6, and we go out 2 units. And there's where our point is. This is roughly the same as the rectangular, or is exactly the same as the rectangular coordinate -3, +1, negative root 3. Okay, example 8b. We have a rectangular coordinate, and we want to convert it to polar. So we can look at our table, and we see that the radius is equal to the square root of x squared plus y squared. And in this case, that would be r is equal to 3 squared plus -3 squared, or root 18. So we now have our radius. Put that down here, root 18. And then we need to find our angle. So our angle, tangent of theta, is equal to y over x. So we'll write tangent of theta is equal to -3 over 3, or tangent of theta is equal to -1. And we want to know the angle that tangent of theta is equal to -1. And applying inverse trig operations, we're taking the inverse tangent of -1, and looking at our unit circle, we see that this occurs at 3 pi fourths and at 7 pi fourths. And so there's two possible answers here. Let's turn to thinking about this visually to determine which one it is. Our xy pair is out 3 and down 3. So that tells me that we're at the 7 pi fourths angle. So that's the angle we want, and we get 7 pi over 4.
I mean next Tuesday. Hey, you there? What? Hey, what? There, there. Hey, hey, you there? There. Hey, there, there. Oh. Hey, you there? Okay. I see you over there. One time I want you to come here. Sit down.
Okay, in example 9, we are converting from a rectangular equation to a polar equation. So without further ado, let's just tackle these one at a time. The first problem, we're going to sketch y equals 3x minus 1. That's a line of slope 3. Looks something like that. And we want to convert that to a polar coordinate system. So we know we can replace y with r sine of theta. And we know that we can replace x with r cosine of theta. And we now have a polar equation, but usually polar equations are going to be expressed as either r equals or theta equals. So let's try to solve this equation for r. Let's isolate r by moving all of the r terms to one side of the equation and all of the non-r terms to the other side of the equation. That will allow us to factor a r out of the equation, or the left side of the equation. And now that we've factored the r out, we can isolate the r by dividing. -1 divided by sine theta minus 3 cosine theta. All right. There we go. Which equation is easier to read? The rectangular equation or the polar equation? I definitely would say that in this case the rectangular is easier to use and easier to operate and perform calculus on. Okay, let's try the next one, part B. Y equals 2, that is a horizontal line at 2. I don't know why I'm dotting it. It's a solid line at y equals 2. And we want to set this up in polar coordinates. So we know that y can be replaced with r sine of theta. There's nothing to replace on the right-hand side. And then we just want to solve this equation for r. So we get r equals 2 divided by sine theta. And we know that 1 over sine theta is the same thing as cosecant theta. So r equals 2 cosecant theta. There we go. There's our polar equation. It's not a terribly difficult polar equation, but I do think the rectangular form is easier to work with. But there might be needs for the polar equation. Okay, finally moving to example C, or 9C. X squared plus y squared equals 9. We know that this is a circle of radius 3, or we should know. So if we were to draw in our circle, oops, I missed that value. There's what that curve looks like. This is not a function. We can see that it does not pass the vertical line test, so it is not a function. At least not a function as a rectangular function, but it might be a polar function. So let's try to solve this using polar coordinates, or write it as a polar equation. We can replace x with r cosine of theta, so x squared plus, and then sine is, or y is r sine of theta, so we replace y with r sine of theta equals 9. And going about solving this equation for r, we can first distribute this square in, so r squared cosine squared plus r squared sine squared. Then we'll factor a r squared out because our goal is to isolate the r. Cosine squared theta plus sine squared theta. And there's a Pythagorean identity right there. Cosine squared plus sine squared is the same thing as 1. And we wind up solving this. R is equal to 3 by taking the square root of both sides. There you have it. Radius equals 3. That is a very simple equation in comparison to the rectangular equation. So performing calculus on this equation is probably easier, depending on what type of calculus you're performing. Okay, let's try to do the example 10, where we're taking a polar equation and going to rectangular. So we might recall from the last lesson that the equation of the number times cosine theta is going to trace out a circle. The number gives us the radius, or sorry, the diameter of the circle. So this is what that curve looks like. It's centered on the x-axis because of the cosine, and the diameter is 2 units. So let's try to create an equation for this. We know that x can be expressed as, r can be expressed as the square root of x squared plus y squared. And we know that cosine of theta is the same as x over r. And we haven't gotten rid of all of the r's yet, so we're going to do one more substitution. X squared plus y squared is left alone, 2x, and then the r becomes, again, x squared plus y squared. And solving this out, we're going to try to get this into a y equals form. So we're going to multiply the denominator across, and that gets rid of the radicals. And then we can move the x's to one side of the equation. And this is probably the best you can do as far as having a single expression, but if you wanted to, you could break it into two separate expressions and say that y is equal to the positive and negative square root of 2x minus x squared. So both of them have their merits. If you were asked to solve for y, this would be your answer. If you were just told to write a rectangular equation, at this point you're at a rectangular equation. Actually, even any one of these three, you're a rectangular equation. But I'm going to have us try to aim towards solving it for a single variable, either y equals or x equals. Part B. Theta equals 3 pi over 4. So that's saying we go to the angle 3 pi over 4, and we're going to draw all of the available radiuses. So we wind up getting a line that looks like that, which right away we should be able to say that is the equation y equals negative x. But let's go ahead and try to solve this equation using our conversion techniques. We have a theta, and we do know that tangent of theta is equal to y over x. So tangent of 3 pi over 4 is equal to y over x. And that means tangent of 3 pi fourths is negative 1. And there we have negative 1 equals y over x, or simply negative x is equal to y, which is what we predicted. So comparing those two equations to each other, the polar form is a pretty clean equation, and the rectangular form is pretty clean. I think you could really work with either one of those in this case. Finally, r equals cosecant of theta, and I have no idea how to graph this one, or I do, but I think the easiest thing is to try to convert it first and see if we can graph this more easily in rectangular coordinates. So what we have here is r equals cosecant of theta. I prefer dealing in sine and cosine, so I'm going to change this to r equals 1 over sine of theta. And then I can multiply the denominator out, and I get r sine theta equals 1. And at that point, I see that r sine theta, and I know that that is equal to y. So y equals 1. There we go. That's an easy equation to draw. Y equals 1. It's kind of like the problem that we did example 9b. We had y equals 2 became 2 cosecant theta. And here we have y equals 1 becomes 1 cosecant theta. So we probably have a general rule to be learned from there. Y equals m becomes m cosecant theta. Okay, after this lesson, hopefully you can convert from polar to rectangular or rectangular to polar. Some important equations to remember is that x travels with cosine, so x is r cosine theta, and y travels with sine, so r sine theta. The mnemonic I have is y and sine are both kind of stretched vowels. Let's see, some other equations that we should have picked up. R is equal to the square root of x squared plus y squared. And we should also know that tangent of theta is equal to y over x. So those are the four formulas that you should memorize and be able to manipulate for tonight's or the homework associated with this, and polar calculus in general. Thanks for watching. Enjoy your evening.